Hi, this is Dane Quinn from the University of Akron, and today's lecture for dynamics will consider planar kinematics. So, in general, kinematics is the consideration of the allowable motion of an object. Right? So the idea is what could an object do? Right? Not necessarily what it does, but what could it do? So this has to be consistent with the constraints that act on that object. So if there are sliding constraints or parts of the object that are pinned, the kinematics have to reflect that. And in particular, without regard to the forces that produce motion, or the motion that actually occurs. So again, we're looking at the allowable motion, what could possibly happen. Because, as part of dynamics, the kinematics looks at what could happen, then we look at the forces that are applied, then the equations of motion tell us what actually does happen. So again, let's start off with a description about rigid bodies. Right? So dynamics concerns the dynamics of rigid objects. So what does it mean to be rigid? Well, we're looking at objects that have no internal deformation. So here, what that implies is that the relative distance between any 2 points remains fixed. And so if we kind of look at, say, 2 points on an object, and these are any 2 points on the object. Right, let's call them point A and point P. Then the vector from A to P, right, so we'll denote that by this position vector, is fixed in the object. So again, relative distances are constant. Again, this is all obviously in terms of the object itself. So in particular, if I were to go and describe, say, vectors, basis vectors, E1 and E2, that were fixed in this object, B, then I could go along and say, okay, the distance of position of P with respect to A in the E1 direction might be a distance S1. Then in the E2 direction, might have S2. So what this means is that this position of P with respect to A is S1 in the E1 direction plus S2 in the E2 direction. And then these distances, S1 and S2, are constant. So that's what it means to be a rigid object. Now, of course, the object itself could move around. So these basis vectors, E1 and E2, which are fixed in the object, could move relative to the ground, but the distances in the object itself are fixed. So now, if I have a rigid object, then one of the things that we're interested in is the configuration of the object itself. And so how do we describe where the object B is? Well, we're going to do this in general for planar objects with 3 coordinates. And essentially, it might be the position of A. Right? So let's imagine that we have an origin out here in the ground. So then I can describe the position of A. Right? So this would be the vector of A with respect to O. So again, here, really we're talking about this position vector. And then we can relate that and the rotation of the object. So here, this is essentially the orientation of E1 and E2, those directions that are fixed in the object with respect to, say, directions I and J fixed in the ground. So this is going to be sort of represented by the angular velocity of the object. So now if I look, this is going to have two coordinates. And then the angular velocity will be one coordinate. Of course, this is for planar dynamics. So these are objects that only move in the plane. If we have full three-dimensional kinematics, then we'll actually need 6 coordinates. 3 would be associated with the position of some point on the object, and then 3 more would be associated with the rotation of that object in space. But again, for planar dynamics, this point A can only move in the plane, right? So we have 2 coordinates that describe its location. Then the rotation of the object has to be about a spin axis that's normal to the plane or out of the plane, right? So that's only one angle to describe the orientation of this object. So again, rigid bodies have no internal deformation, and the configuration of a rigid body is described in terms of, say, 3 coordinates. So now, in general, objects can translate and rotate, which means that any point on the rigid object has a different velocity and acceleration, or could have a different velocity and acceleration from any other point. So, for example, if we have this object, this point could move in that direction, and this point could move in that direction, and that point could move in that direction, and I could go along and describe the velocity and acceleration of any point on this object. And they all have different velocities and different accelerations in general, right? Which is going to have important implications when we start talking about momentum balance, right? Because some of the forces is mass times acceleration, and each point could have a different acceleration. So really what we'd like to do in planar kinematics is the following, right? So for this object, B again, let's look at a point P, say here on the object. And so the idea is to express the motion of P and so by motion of P, what we really mean is the position of P with respect to the origin, right, that's fixed in the ground. Right, so let's put the origin there, and let's look at this position vector. So we'd like to express the position, but then also the velocity of P and the acceleration of P. So these are the things we're interested in: position, velocity, and acceleration of P with respect to the ground. But we want to do it in terms of the configuration of the object, right, which essentially amounts to the motion of A. Remember those 3 coordinates that we talked about before. Some point A, right, so let's put A there and describe the vector of from O to A, like so. So again, we have the motion of A, so that's going to be r of A with respect to O, and in particular the velocity of A and the acceleration of A, and the rotation of the object, right? So, and that's really going to be the angular velocity and angular acceleration of this object. And so maybe it spins with some angular velocity and acceleration. We also have the motion of A, so we'd like to express the motion of P in terms of essentially the motion of the object together with then the relative motion of this point with respect to the object. So the relative motion of p with respect to a. So what happens if we know how p moves in the object? Or even better, if p is fixed in the object, then we can draw the position vector like so. And this would be, of course, r of p with respect to a. But we also might have p moving in the object in some known way. So we could have the velocity of p, not with respect to the ground, because that's what we're trying to find, but with respect to the object. And then we could have possibly the acceleration of p with respect to the object. So again, planar kinematics is about this, expressing the motion of any arbitrary point in terms of the motion of the object itself, together with the relative motion of that point with respect to the object, or in this case, position of p with respect to a, and then the velocity of p and the acceleration of p, both written in terms of the object itself. So that's kind of the goal of planar kinematics, because if we can do that, then we no longer have to describe coordinates necessarily for each individual point on the object, right? We can look at, in particular, if the object, if the point is fixed in the object, we can just look at the rotation and translation and kinematics of the object itself in terms of these pieces, together with, say, some known position vector, RPA. Okay, so now what we'd like to do is consider the following case, which is namely A and P, the 2 points that we have fixed in the object. So we'll again put A over here, put P over there, and then we will define the origin over here. So now we have the position of P with respect to O, right? That's this vector. And again, that's what we're interested in. And we'll write that in terms of the position of A with respect to O, plus then the position of P with respect to A. So now this little relationship can be written as R of P with respect to O is R of A with respect to O plus R of P with respect to A. Right, so again, this vector is simply that vector plus that vector. And now if I want to find the velocity of P, I'll take a derivative. Right, we'll look at how this changes, just like always. So it's the derivative of the position of P with respect to O. And again, we're taking the velocity in terms of the ground. So O is fixed in the ground, P is the point we're interested in. Well, let's go ahead and write that using this vector equation. So it's R of A with respect to O plus the change in R of P with respect to A. So now we can go and evaluate these two terms. And we see that the velocity of P, well, this first term is simply the velocity of A, right? It's how this vector changes, right? So that's the position of A with respect to O. So again, that's the velocity of A. Now this next term, it's the change in RPA. Again, because A and P are fixed in the object, this vector has fixed magnitude, but the direction changes. So we've already done a lecture on vector derivatives and looking at how vectors change. And one of the things that we learned then was that if you have a vector of fixed length, then the change in that vector is simply the angular velocity cross the vector itself. So again, this is the angular velocity of the object, or it's how fast this vector spins. Right? So this is simply the velocity of p. It's the velocity of a plus omega cross r. And again, if a and p are fixed in the object, then this expresses how their velocities are related. So now, of course, we can go to the next step and look at the acceleration. So we have the acceleration of p is just the derivative of velocity now. So that's going to be the derivative of this equation up here. So first term is the derivative of the velocity of a, and then the second term is the derivative of what's left, which again is omega cross rp with respect to a. So now, as before, this first term is simply the acceleration of a, right? Because again, we have the derivative of velocity of a. And then this next term, we're going to use the product rule. So in particular, it's the change in the first term, omega cross r of p with respect to a, plus omega cross then the change in the second term. And so again, this is simply the product rule applied to this cross product. Right, so now we can simplify this, and we see that the acceleration of p is the acceleration of a plus this stuff. Well, the change in angular velocity is just the angular acceleration, right? So we have alpha of the object cross r p with respect to a, and then omega cross this term. Well, we've already done that, right? We saw that before when we evaluated the change in RPA, and it was omega cross r, right? So it's still omega cross r. And so now we have a relationship between the acceleration of a and the acceleration of p. And as before, this is valid anytime a and p are fixed in the object, fixed in beta. So this last piece is known as the centripetal acceleration. And in this cross product, omega cross r, must be evaluated before we cross with omega. Right, so this omega cross r term must be evaluated first, because the cross product is not associative. Right, so that piece in the parentheses, we have to work that out, and then take the cross product of omega and that resulting term. I mean, otherwise, omega cross omega would be simply 0, right? So this term would vanish if the cross product was associative. But it's not, and so we have to do this first. So that's how we relate the velocity and acceleration of 2 points that are both fixed in the same object. Now, the next case that we'll look at, and sort of the most general case, would be what happens if p is able to move in this object. Right, so now, let's let a be again fixed in the object. With p moving on some path. So again, well, so let's assume that we have some path for p, right? So p is going to move along this dotted line. We'll have A there, we'll have P there. Again, we'll put the origin O here. But again, p is no longer fixed in the object. But we assume that we can say something about the motion of p in the object. So once again, we have the position of p with respect to O. We have the position of A with respect to O. And we have the position of P with respect to A. So here, we still have the same relationship between these three vectors. R of P with respect to O is R of A with respect to O plus R of P with respect to A. But now, this last vector is no longer fixed in the object. Instead, it changes, right? Even when expressed in the object. But looking at the velocity, we can find that the velocity of p is the derivative, as before, of rp with respect to O, which is the change in Ra with respect to O, plus the derivative, or the change, in Rp with respect to A. So now, we have some additional terms when compared to the case where p was fixed in the object. That was the last slide. But this first term is exactly the same. It's still the velocity of A. Now, this second term, right, again, we can go back to our expression for vector derivatives, and we see that it's the angular velocity of the object cross RPA plus now the change in RPA with respect to the object. So again, let's add some directions here, E1 and E2, that are fixed in this object. And then let's look at what this term means. Well, what it actually represents is the velocity of p with respect to the object. So the idea kind of is, imagine you were a little bug, right? So there you are. And you're standing in the object. So as the object moves around, you move along with it, right? Because again, you're just standing in the object. And so what do you see? Well, you see p moving around. And you see the velocity of p, in particular with respect to you as the bug, as the change in RPA. Right? So again, that's what this term represents. It's the change in RPA to an observer that is fixed in the object. Right? So the way we write that is that the velocity of p is the velocity of A plus the angular velocity cross RP with respect to A, plus finally the velocity of p, not with respect to the ground because that's what we're looking for, but instead with respect to the object. And this is the most general expression for the velocity. Now, when it comes time to go and evaluate the acceleration, right, we'll basically do the same sort of thing. The acceleration of p is the derivative of velocity, which ends up being the derivative of all these terms. Right, so it's the derivative of VA plus the derivative of omega cross RPA plus the derivative, or the change, in the velocity of p with respect to the object. Okay, so now we can go through and express each of these terms. And this first term is, again, simply the acceleration of A. So this second term, we will use the product rule. So it's the derivative of omega cross r plus omega cross the derivative of r. So that's going to be alpha cross RPA plus omega cross, and now again the derivative of RPA, which, look, we've already done that. That was simply omega cross RPA plus now the velocity of P with respect to the object. Again, that's what we had from our previous step when we calculated the velocity. And now it's the change in the velocity of P with respect to the body. Again, going back to our discussion on vector derivatives, this is the angular velocity of the body cross the vector itself. And then finally, the derivative with respect to the body of the vector. So we can now combine some of these terms and say that the acceleration of the acceleration of P is the acceleration of A plus alpha cross R, P with respect to A. We'll have the omega cross R term that we saw previously. But then we have two new terms. In particular, we have an omega cross the relative velocity term here, and then we actually have the same term here, right? So we have two of those. So it's 2 omega cross the velocity of P with respect to the body. And then finally we have this last term, which, just like this became the velocity of P with respect to the object, this term becomes the acceleration of P with respect to the object itself. So this is now our most general form for the acceleration of P in terms of the motion of the object. Right, so that is encompassed by the acceleration of A, the angular acceleration of the body, the angular velocity of the body, together with the relative motion of P, because now P is moving around in the object, with respect to the body itself. So that's the RPA, the velocity of P with respect to the body, and the acceleration of P with respect to the body. Right, so again, this term represents the centripetal acceleration. And this 2 omega cross V term represents the Coriolis acceleration. And this term is responsible, for example, for the spin of hurricanes, for the rotation of hurricanes, and how it's different in the northern versus the southern hemisphere. It is not, however, responsible for the swirling of toilets in the northern and southern hemisphere, as popular myth claims it to be. That actually has to do more with the design of the toilets and not the Coriolis acceleration. But it is important for large-scale dynamics, such as hurricanes. So this is our discussion of planar kinematics. Right? We've talked a little bit about rigid bodies, and we said the goal of this is really to express the velocity and acceleration of any point in the object. So here we've named that point P in terms of what's happening with the object, together with what happens to P with respect to the object. And again, that tells us what happens to P with respect to the ground. And we've done that in two cases. On the previous slide, we considered both points to be fixed in the object. Right, so then we had these two expressions. And then the most general case is when P is allowed to move in the object. And of course, if we take these two and then assume that P is fixed, this term would drop out, and then these last two terms would drop out, and we would recover what we had on the previous slide. So that's our discussion of planar kinematics, and of course we'll do some examples, and we'll later see how this is very important for obtaining the equations of motion for linear momentum balance and angular momentum balance for rigid objects. So thank you very much, and I will see you again.